Mobile app hacking and mobile application security is an awesome field and piece within the cybersecurity industry. But there is a lot to learn, and it can get a little bit complex. So, what I'd like to do is walk through one simple and small example, little demo and showcase with an Android application written in Java. And we'll walk through 3 different attack scenarios where we could maybe extract and uncover some secrets, sensitive information and data, maybe API keys, passwords, and credentials, and actually tamper with the application. Maybe modify some of its behavior and dig into how we can beat up and do some damage against a mobile app. This video is sponsored by GuardSquare, and I'll tell you more about that later. Now, before we actually dig into the code, I'd like to show you this app in action, just so you know what it looks like and everything that we're up against. So what I will do is drag this uncrackable secretsafe.apk file into our Android emulator that I have set up running with Android Studio. You might have seen it did say it was installing that APK. Now, if I swipe up, we do have our uncrackable 1 app here. I can click on this, and this is it. Small, simple example, just an app for our learning and demonstration, but all it's asking for is enter a secret string. Now, we don't know the secret string, so I could enter, I don't know, whatever I want. Maybe please subscribe, ha ha ha. I'll click verify, and that'll tell me, nope, that's not it, try again. But that is all the functionality of the application. We're just trying to check, hey, can we figure out a password? And again, maybe you could use this. Maybe we're laying the foundation for other mobile app hacking techniques to track down credentials, API keys, other secrets, or actually hook different parts of the application's logic so we can get in the middle of it and do whatever we'd like for our own analysis. With that shown to you, now we can close out of our uncrackable 1 app and then start our analysis with some of the source code. So first things first, let me open up a command line. I do have a Windows terminal and PowerShell prompt open and available for me. I'll hit F11 to bring that to full screen, and I'll move into this directory. I've created a folder for us in C:\APK. That is where I have this uncrackable secretsafe.apk or Android package file. Now, what I'd like to do, honestly, is start with some static analysis, and we'll use the tool JADX in the GUI representation to do that. I'll hit enter here to fire up that application. And super quick, just in case you aren't familiar, JADX is free and open source software. You can find it online at GitHub, github.com/skylot/JADX, and it is a Java decompiler. We could actually scroll down to see a little bit more of the README. It is a command line and graphical user interface tool for producing Java source code from Android decks and APK files. That's exactly what we need, and we could actually drill down into a lot of the source code. Super cool. You could download the releases and actually get this thing in action with either the command line or the GUI instance. Now that JADX GUI has opened up, let me drag that window in so it's visible. We'll maximize this, and I want to click on that open file button here. With that, I'll navigate to our C:\APK folder, and I'll have my uncrackable secretsafe.apk present here. We'll go ahead and click open on that. And now it should be able to decompile and extract out some of the resources, manifests, and all the cool information from that APK. Everything inside that Android package and that Android app, right? So let's drill down into the source code. That's where stuff gets kind of interesting. And this is a learning example application, bear in mind. So we see this owasp.mstg.uncrackable1 bit here, another package. We could expand this, take a look at some of the classes. However, this is noted, if we actually scroll down, there's a lot of interesting things here. This is set as a little comment, JADX info. This class is generated by JADX. So I don't think that's super duper helpful for us. We don't need to spend a lot of time there. There's not a whole lot of worthwhile, interesting things. It's just something that, hey, we could still be clicking around trying to see what else is available here. But let's continue on and let's go take a look at this sg.vantage point. Let me expand this. We have another package here for the letter A, and then all these classes included. And this has a little bit more interesting stuff. There is presumably going to be some cryptography in the mix here. We're loading some cipher capability, being able to create a secret key based off of AES. That's good to note, but we do need to actually track down how this all comes to life. Let's go explore B, and all this is getting the application context. Okay, nothing all that interesting there. How about C? Ooh, This has just a little bit more code, but none of this exactly kind of lines up with what we saw when we clicked around and played with the app within our Android emulator. So I am going to table this for the moment. B and C, we don't really particularly have to worry about, I think, but A is interesting because it's going to do something with the secret, do some cryptography, work with ciphers here, but let's drill down to that uncrackable one package here and see, okay, how does this actually match what we might have seen when we open the application? You might already be familiar, the main activity is usually where everything kind of starts for an Android app. So we could actually take a look at what is happening here. Void A is a function that defines an alert dialog to create and set a title based off of a given string, set a message where we're saying this is unacceptable, this app is now going to exit. Okay, set button, system click. We didn't see that happen. A, I don't think actually ever ran when we got to see it in action. Oh, but actually scrolling down, we can see an override kind of set up here on create. We're checking, oh, that C function that we just called. Okay. So everything previously was to check and see if that was actually running as root with a couple different tests of, oh, maybe files that exist like superuser.apk, daemon.su. That's cool. Kind of a clever, small little way to check if you have a rooted device. And I guess that's the gimmick getting in the way here. Nice. So we know that we won't as easily be able to test this in like a debugger or the root being detected because it's going to exit and whine it right away. Unless we were to tamper and manipulate that, which we could do at runtime. We'll explore that later, but let's go take a look at the other functions here. Now that we know that that error was just if it were being debugged or it found root. Verify, though, we could take a look at this. Verify will take in a view. Looks like it'll display based off of some information that we provide in our text edit, like input box, right? And it will use A.A, given some info, and then display a success, whether that's the correct secret or nope, that's not it, just as we saw. Okay. So this must be the actual logic for validating and knowing that our verify function was a piece of it, and that's really how this all comes to life, but A.A is where this comes to life. What is in A? That's another little class name, granted A, but inside of the uncrackable one package. So here we go. Look at this. We can see public class A, public static Boolean string, working with a byte array called BR, which I'm going to assume is where this gets populated as it fills out, trying to, work with the secret cipher that came from A.A.A, with B wrapped in the mix of this, base64 decoding some things based off of cryptography. So a secret key, some data that it decrypts, and then it will check based off of our input that's provided, passed in as a parameter. If it's equal to what this decrypts and evaluates, then that is the correct secret, which means BARR is the actual plain text value of the secret. We need to figure that out. We need to track down what that secret could be, what that API key might be, what those passwords or credentials or some sensitive information that we want to get in the middle of. That really is all the logic of this app, though, so something that we could do is actually try to recreate it in our own testing instance, our own app using the same code so that we could change, manipulate, and print out what that secret info might be. Let me open up Android Studio, we'll have that here, and let's just create a new project. And of course, if you don't have Android Studio installed, you can download it online from developers.android.com. Super easy, just the executable or whatever platform you're on. Let me move this over to the side so it's a bit easier for you to see. And in the phone and tablet section, I want to actually click into the empty views activity. And I'll go ahead and click next. With that, we can rename this to whatever we want. We can just call it like app. We'll put it in the C:\APK folder. Let's set the language to Java, as that is what we were working with in the original uncrackable secret safe. And I do want this to be on Android or APA 33 Tiramisu, because I believe that's what I was using for Pixel 6, the emulator that I had open. So let me go ahead and click finish down on the bottom right. With that, it'll open up a big window trying to do a whole lot of stuff. You'll see the Gradle project sync in progress up here. So it's going to do whatever Android Studio does to kind of prepare a couple of these things here. But now let's see if we can actually get this to run. Let me toggle this to make sure we are running on our Pixel 6 Pro as we were. Let me hit the play button, and fingers crossed, we'll open up our emulator and then see this in action. I think I can go over to the device manager over here. Okay, it has spun this up here. Looks like that is going to be created and turning on. I might have clicked around too much, so I'm going to press play one more time. Now we'll see our Android app open, and you can just barely see Hello World down there. Okay, so it is running. It is doing as it should. And down below, we did get to see, hey, maybe the logcat panel for the emulator. So we could, if we wanted to, just simply print out text here and have that displayed. So let's see if we can honestly just genuinely print out the secret as it is decrypted. That means if I close out of the running devices and get back to editing the code here, we could just like paste in chunks of the code that we saw in JADX and then unravel the secret. So jumping back into JADX, we know this B array variable is what ends up ultimately decrypting the data. So we need to be able to recreate this function call, which means we have a couple imports. We want util base64 and log. Let's get those. Jump over to Android Studio. We can slap those in. And let's grab the contents of this A function and let's go put that in and kind of work with it, because ultimately our onCreate, we want to be able to have this still run. We don't need our B array 2. We'll have to change these names here because we actually want to call a function not in a separate class or package, but actually one that we'll define here. And we probably don't need to do any of this. We can just add a system out print line error decrypting or something, and then we can do the very same at the bottom to actually print out the secret string is, and then we'll concatenate on a new string of our B array, as it would have been decrypted with these functions A and B that we will create. Now, A, as you saw, was actually referenced in the sg.vantagepoint package, so all of that nonsense, we actually want to go grab this syntax, and let's go ahead and make sure we can create and do that. Let me grab this function, not the class, because we are already inside of a class in our main activity, but let's go create inside of another function, that. Now there's a lot of stuff that we will need to import here. Let's go ahead and get those two and bring those in just as well. Scrolling back down, we still have a couple red squigglies, so get instance is not happy, init is not happy. I think we can just add the imports for all of the things that we need here. So Java security invalid key exception is something that we want. Import Java security invalid key exception. That should clean up our init function, right? Oh, even if we've imported those things, I think we should still add try and catch statements around there. And we'll do the very same for these others. Fingers crossed, that is looking okay. Now we just need the B function added in. That is where we came from the A class, though. We did see public static byte B just to do some stuff with the length. So let's copy and grab all of that. Go ahead and paste that in under our A function. No complaints, no errors there. So let's see, do we have any other issues? I think we're A-okay. Oh, it does still want our B array variable to be initialized with something. So, okay, that's fine. Let's add that there. How about now? Let's press the play button and see if we can get this thing in action. Okay, firing back up. Install ran. Now, if I open our logcat panel, do we get to see any of our output from running this thing? Oh, there it is. The secret string is, I want to believe. Okay. Now, I know that's a small, simple, trivial example, but it does go to show with, okay, look, we can kind of piecemeal and uncover what might very well be a password, credential, API key, anything. Now that was technique number 1. We got a couple more to cruise through because bear in mind, we did all this just statically, with static analysis, taking a look at the code, maybe trying to recreate it in our own testing sandbox instance. But what if we could do this dynamically, do some dynamic analysis and actually hook into function calls, tamper with the process and the actual functionality of the application by making it do different things as we kind of laser focus on one specific function call. Like in this big A function that we saw was actually kind of validating and verifying after it has decrypted our secret sensitive string. It does this str.equals. That's the simple check if the string that is passed in as an argument is equal to our new string of the B array, the byte array that is the decrypted value here. So what if we could get in the middle of this str.equals function call? We can try and hook that with Frida. If you aren't familiar, Frida is gosh darn incredible. I'm online at frida.re, and it is a dynamic instrumentation tool for developers, reverse engineers, and security researchers. You can script it, you could do whatever you particularly want on any of these little functions. Super easy to install, just pip and Frida tools, and then you get up in action. Tons of documentation if you'd like to explore a little bit more. Hey, take a look at some of the tutorials, see some different examples in different platforms, different languages work. So very, very cool stuff. And we will finally open the door for Frida, which I've been wanting to do for forever on this channel. And let's play with it. So back on my command line, I do have Python actually available for me. I do have pip actually available for me. So all that I would want to do is, just as you saw, pip install Frida tools, and that will pull it down. I believe it is already installed. Yep, looking good. But you might want to do the very, very same. We could pip install Frida, and that will get us all cooking. Again, already staged and set for me, but those are the commands you might need. And to validate that this is running and accessible for us, I can just run the command Frida. But that will need a little bit of other arguments here. You can see the usage, Frida, and then some options and a target. If I actually run Frida tac h to get the help options, see what is available to me, there is a lot of stuff here, but ultimately you'll probably want to end up using the tac capital U. That'll work over USB to connect to an emulator, in which case our emulator through Android Studio is acting like a USB device. So that's kind of the easiest thing for us. So I can actually use one of their convenience scripts like Frida PS that should just display the running processes. And remember, we'll use that tac capital U to work through that on our emulator. Once I hit enter here, it'll pull down everything it seems to be running in our Android emulator. Do we have our app in here? Maybe it's still up in action. I don't know if it's still running. Scrolling up to the top, it's not there. Maybe I close out of it. That's okay. Let me show you it in action here. We can interact with our emulator just however we would like, right? So if I actually open up even the uncrackable app, let me run Frida PS one more time, and you'll see now we have the uncrackable app available. Scrolling up through the output here, we do see our uncrackable app is running, in which case Frida is working. It's connected, and we can do what we'd like. So everything that we've had so far in this directory is our uncrackable app, the original APK itself, our testbed app as we were working with in Android Studio, but now I want to put together a small little script where we can hook our str equals function with Frida. Let me open that up in Sublime Text as a text editor. Now that that is open, this is working in JS or JavaScript, but the syntax is pretty simple, and if you aren't too familiar with it, you can always just ask ChatGPT, and I'm positive it will churn out some results for you. I want to use the Java object and then perform, wrapped inside parentheses there, a function handler that we'll create, where we can actually grab the string class from Java if we want to use the Java lang string type. Make sure to end that with our semicolon here. Now we basically have access to all of the functions, methods, and things you can do with string type objects in Java. So what if we actually were to make some changes to that equals function that we saw, where we set the implementation of it to something else? We'll define it as a function, and you know that would take in the other variable that was, hey, actually being compared to in that equal statement. So let's fill out the function here, add the two curly braces to define the body. And then I still want it to do the actual normal process and behavior of like checking whether or not it is equal to it or not. So let me say the result, we'll store that as a variable, is actually going to enter this being equals based off of the same other argument that we'll pass in. But I still want to be able to examine or look into the arguments that are passed in to this equals call. So we could just display string equals called, and then with that, we'll showcase all of the variables that would have been included there. This being the starting string that it's testing on against the equals function there. Copying and pasting so we can create a couple more of these. The other value is going to be what we are testing it against, passed in as an argument there. And then let's be sure to see the result just as well. So we'll display that. Finally, we will want to return the actual result as we did determine that just above. So the same, actual functional implementation of what the string equals function should do. But now we've hooked it and we can examine, we'll actually be able to see everything that goes in and out that's actually passed to that function call. That'll tell us the plain text decrypted secret or hidden message. Now that we have written this hook script, though, hook str equals .js, and we want to run that with Frida, there are a couple different ways to get Frida actually up and running. One, you could use a Frida server, but I believe that takes a little bit more effort than actually having a rooted device. In our case, we want to keep it easy, maybe not do that in the moment, so we'll use something that can actually inject Frida into the app, which means we'll have to make some changes. That is a little bit easy, though. You just kind of need to, hey, track some of the dependencies or some of the tools that you'll end up using to put that all together in your own new APK. You will need to make sure you have some binaries like APK tool. We'll have that in your path. If you're on Windows like I am at the moment, you can use Chocolatey to install that. Choco install APK tool, have you ran that as administrator, and you'll probably want to do that for like getting a JRE or Java runtime. I tend to use OpenJDK 17. That'll also still get a lot of the development kit stuff as well. I am sure I'm going to get some flack for being on Windows, and actually, if we want to use some of the tooling here, we will need to track down where you have part of the Android SDK or the software development kit on your machine. So I actually want to drill down to the platform tools where we have adb.exe, like that Android debugger. We'll want to make sure that is in our path. So let me export, or no, I'm in PowerShell, sorry. env path should equal our env path, the semicolon to now access platform tools. So now ADB should be something I can run without an issue. That is not the end of it, though, I will admit. If we actually want to go find the other build tools, there are a couple of versions that might be important there. You'll see there are a couple different renditions. I think 34 is the one that's been working the best for me in my case, because I want to be able to go track down, I think AAPT, AAPT2, and the others, and that also will include apksigner.bat, which we will need to end up using next after we build an entirely new APK file that has Frida injected into it so we could have our hooks working. So let me stage that as part of my path just as well. Separated with a semicolon, we'll include that there. And now I can use, I think, apksigner.bat and autocomplete perfectly fine. But now we are just about ready to use Frida to hook this app. We have our hook script put together in JavaScript. We have our dependencies all set up. What we need to do is have an APK file with Frida injected into it for it to do whatever it might do. And there are some other easy tools that allow us to do this. In case you haven't heard of it before, this is an awesome utility called Objection, put together by SensePost. Again, you can find it on GitHub. It is a runtime mobile exploration tool where you're able to quickly and easily just slap some of the Frida functionality into your APK. Now, all we need to do to install it is pip, once again, pip install Objection, and then you run it. That's kind of it. Oh, and by the way, there is a pretty awesome write-up on Objection over on Hacktricks. They include a tutorial with an app to download if you wanted to take a look at it. You could figure out some basic connection, basic actions, being able to move files up and down, do some things to execute commands, screenshots, all the sweet stuff to interact with your emulator and start to tinker and dynamically explore all the apps, creating hooks, sweet, sweet stuff. So definitely recommend you take a look at that. Hopefully trying to give you some more resources. So if you wanted to do that, pip install Objection. I do believe I do have that staged, looking good. Anyway, what we can do, since we have our original APK for the uncrackable secret safe in our current directory, let's run Objection with the subcommand to patch APK, given the TAC-S source here for our uncrackable secret safe.apk. I'll go ahead and hit enter on this, and fingers crossed, if we've got this all staged, all the dependencies are working with our path, binaries, and commands that we want to be able to run. It looks like it's coming together, and now we have a new file in our current directory called our uncrackable secret safe Objection. That is what has Frida ready and available for us. You can see the binary obviously is much bigger because it's packed a whole lot more in there, but we aren't quite able to just slap this into our emulator yet. We will need to actually sign it so that it's able to run without an issue inside of Android. That is why we wanted to have that apksigner.batch script in our path so we could easily run that. We'll use the subcommand to sign. And we do need to supply a key store, so we'll use tac-tac-ks. What you can do is actually use the debugging key store that should be available and already accessible on your desktop because you have Android Studio installed, and that's actually in a user profile, like your C users John or whatever your username is. There's a hidden directory there called .android, and that contains a debug.keystore. I hit tab to autocomplete that so you can see it evaluate. The moment I hit enter here, oh, duh, we will need to actually supply our uncrackable secret safe objection.apk. Keyword there, you do want to use the modified one. Let's hit enter there. Now this will ask for your password. It's not asking for your password, it's asking for the key store password. And since we're using the debug key store, I believe that is a static string for the word Android, so be careful typing that in. It won't show it to you. Echo will be turned off, but I have enter. Okay, no output, no errors. If anything, now we have that signed. You can see the ID sig present there, and this APK file should be good to go. Now let's get back to our emulator and then start to put these puzzle pieces together. Let me go ahead and move this to the side. Let me move our command line over to the left, and I'll actually dock this to the top left, and then I'll open up Windows Explorer in the current directory, just so we can easily drag in our APK. I'll go bring that over here. And before I do all this, I do want to try to uninstall everything. So let me go ahead and click and drag and uninstall the old app. That's fine. I'll do the very same for our testing app. We'll go uninstall that. And now what I want to try and do is actually grab our uncrackable secret safe.objection APK and drag that in to see that install, looking good. Now it's present again, our uncrackable one. The moment I click on this, it's actually going to hang at the icon because it's going to wait for Frida, the hooking language, the instrumentation tool, to actually hook and, hey, grab control of the process. So we'll need to do that over in our terminal in the top left. Now we can finally run Frida. Don't forget, we'll use that TAC capital U to specify the emulator here, connected via USB or a USB device emulator through Android Studio. We'll use TAC L to actually specify our hook str equals .js file. That's our JavaScript. Remember, that's our code to be able to hook into the str equals function call. And then we'll pass in our uncrackable one, if I type it correctly. Uncrackable one being that process that we want to be able to manipulate, modify, and work with. So I'll hit enter here, and fingers crossed, connected to the Android emulator. There we go. We can see it running off in the side here. And if I were to actually now work with this, as this is spamming a ton of string equals calls, maybe for whatever processes that are happening, other code in the background here. But let me go ahead and now enter our please subscribe. And once I hit verify, it's checking that. So somewhere in this output, it has now actually checked, hey, is that going to be what it should be? And we'll be able to see all those things in and out. Let me hit Control C to stop this. Looks like it doesn't want to let me, so that's okay. Let's close this in our Android emulator. And with that, we'll see Frida has closed. Let's go ahead and grab all of the output here and now try to go find where we have our call for actually checking our variable. I'm going to get back into my Sublime Text window and paste this all in. So we have all the text here, and let me Control F for my subscribe string. And there it is. We can see our string equals called and checking against the other variable I want to believe, which we know is that hidden secret message. But don't forget, that could be credentials to a backend database. That could be whatever. When we're using this dynamic method with Frida, and Frida is extremely powerful, it can do so much more, and obviously a whole lot better than just like printing strings in the logcat output of Android Studio, right? Think of like bypassing login screens. Think of like bypassing ads or advertisements in an app. Maybe, hey, I don't know, getting infinite points in like a loyalty or rewards program. Maybe you're cheating in a game and now you get infinite health, infinite ammo, you can walk through walls, anything. Especially when a lot of games now tie to like real world money and currency for stuff, for items, like that's kind of crazy. And even if you apply like string encryption or other obfuscation in your source code, you can still track down the decrypted plaintext values during runtime. That's what Frida lets us get in the middle of. And that was trick number 2. Now let's get into number 3, the final thing that we want to showcase here, actually modifying the Smalley code. And just to sprinkle in some background context, Smalley code is sort of that intermediary representation of the bytecode. Hey, the language, really all the operations, things that your machine might end up doing, the Android ends up running. But if you take a look at it in Smalley, it's one representation that's a little bit easier to read. You're able to see it, make some sense of it. It's not like assembly, it's also not pure Java, but it's between intermediary. You might be asking why bother to use Smalley if, well, you have tools like JADX, as we saw previously, that'll give you that human-readable Java code, but you can't recompile or rebuild an app with that specifically. Decompilation gets a little bit messy there, so actually using Smalley to work with this will let you change resources, inject code, and modify things, and then rebuild that whole application, rather than doing like a separate one that we did in Android Studio, right? So we can get back to our terminal once again, and with our original uncrackable secret safe.apk, let's try to use apk tool, which I mentioned just briefly earlier, and we can use D as the argument to like decompile, decode, whatever you want to think of that as, passing in the original APK. Fingers crossed, I'll hit enter here, and that will go ahead and extract everything out of that. You might be super familiar with that in like the world of Capture the Flag if you're playing a lot of those mobile challenges, but now we have a directory created for our uncrackable secret safe. Looking into the files here, we have the Smalley folder, and if we drill down further, we can, hey, take a look at the classes as they're built out there, SG, Vantage Point, everything that you tend to see when we saw it in JADX. But if we actually move into that uncrackable reference here, we do see our a.smalley. That is where we know that logic was in that A class to actually decrypt this thing, right? So let me open that up in Sublime Text. So I'll zoom out just a smidge and we can see a little bit of the logic here, but it notes that there are 5 local variables, locals 5 defined in this public static A method. We can see it setting up some of the strings that we saw present in the code. We actually see some calls for base64 decoding, invoking static functions, maybe actually using the like log.d might have been present there earlier if it had that code check error, anything. Here it is, there's that log d. At the end here, you can see our invoke virtual with that string equals, knowing that it stores this into P0, and that's what it ends up returning there, right? So V1 must be our actual, byte array, that variable that's been tracking, as it's been trying to put this together. So using all of the syntax as kind of a reference, how could we manipulate this? Well, let's try to add our own variable first of all. These are 0 based, right? So there should be V0, V1, V2, V3, V4, up to 5. But let's try to add a 6th variable. So we'll change that total number of locals to 6. And now we could define our own constant string V5. Remember 0 based. So we could say the secret string is, define that as a variable there for us, and then we could just kind of latch onto the other log d that we saw down here with this invoke static. That includes some of these variables, v1 and v0, but what if we were to print out our own v5, the secret string is, and then v1 later, as we know it has just decrypted it. So before it returns all this, we could simply run our own function, invoke static here, and spit that out. Changing the arguments to now v5, our this is the string, and then our secret string, v1. This is peculiar though, because it will move the result into P0, which it ends up returning. So I'm assuming our log D will succeed, give us some good value. So anything that we enter will tell us true success. That is the secret. That's okay. Sort of a byproduct of, us messing with it. But I think that's all we need. I'm saving this file over and over again, and let's try to rebuild this. So let's get back to our terminal. Let me move up, get out of these directories, because now we can use apk tool once again to rebuild this. Let me run apk tool B to build our uncrackable secret safe, hit enter, letting that cruise through it, and that should build this all into that same directory here, now with the dist subfolder. So if I move into there, we can see we do have our uncrackable secret safe.apk, but let me actually rename that to uncrackable secret safe Smalley modified or whatever. And now let's open that in Windows Explorer. If we put these side by side once again, let me uninstall the old app just so we start with a clean slate here. We can uninstall, good by me. Oh, and actually, before we go too far further, we do need to sign this. So I'm gonna hit Control R on my command line so I can search for APK signer and like reverse search. That way I can get our sign syntax, but now let's change this to our uncrackable secret safe Smalley modified with everything present there. Fingers crossed the password is Android. That should be done. And now back in Explorer, we have both of these. I want to drag in the APK file, let that install, looking good. And I do want to make sure I have the Android Studio logcat open so I can see this output as it comes through. Let me move this to the side and bring up our logcat. Now I should be able to see messages as they come through. Let's go ahead and open up our uncrackable one and try to do this as usual. Let's do a Please subscribe. We'll go ahead and click verify, and it tells me success. That is the correct secret. Remember, that was the side effect. We know that would happen. But now in all of this output, we might have to scroll through it. I'm sure we could track it down. Moving back up here, we can see, hey, there's a log D, I want to believe. And once again, we have found that password, that secret, that sensitive information, that API key, that password, that crypto secret nonce, whatever. You can search for this, by the way. If I just, hey, enter filter for secret, we know our output, the secret string is, and there is the uncrackable from the original app itself, not our old one, as you saw us start with. So that's so cool. And that was technique number 3. We modified the code. We modified the Smalley code, all that bytecode intermediary stuff, to do anything. Like, obviously, this was a small, simple example where we just print a static string to standard out. But think about this. Possibilities are endless. You could inject malicious code, like in the middle of a login form, to swipe up the credentials and then push it off to some remote server, like a little info stealer malware flare. You could patch out whatever you wanted to. Maybe you could, hey, unlock any sort of features or like payable unlocks and achievements in the game. You could skip entire progress segments of anything. Now, everything that we've showcased thus far has all been about the weaknesses. How you can take advantage of this, how you can manipulate it, how you can do some mobile app hacking. But I want to talk a little bit about the protections, the defense, how you can amp up security for your mobile app. Because all this that we were able to play with kind of just falls apart when we have a protected app. And let me show you this. I'm going to paste in another APK file. Here it is, our protected uncrackable secret safe. Let me open this up in JADX, just as we've done the others. Inside of JADX, let's go open that file, our protected uncrackable secret safe, and it's going to take a little bit of time to load all this because there is so much more here. If I actually drill down into the source code, let's take a look at the SG Vantage Point uncrackable, look at the main activity. And take a look at all of this, because this is the exact same application. It is now just protected. It has a whole lot of obfuscation, encryption, little security mechanisms, things to help prevent any other analyst, any other security researcher, any other hacker, ill-intended actor, threat actor trying to tamper with, modify, and manipulate this whole application. I know this is massive, but this is awesome because you can't even find all those strings that we saw previously, like, oh, the nope, that's not it, or success, that's the correct secret string. Like, if we were to even try to search for those, I think I might be able to just Control F, right? Success. Probably not in the main activity. Let me do a text search, Control Shift F. That'll bring in another window here, but if I were to search for that success or nope, or any of the things that we started with previously, hey, we don't have that anchor anymore to key off of. The if statement, I mean, good luck finding it for one thing. There are tons of these if statements if there are anywhere. And look, JADX can even compile all this well, or decompile it. There are all of these runtime protections enabled, so much so that in most cases, and I don't know if it is in fact in this app, but if it detects an emulator or if it knows it's on a rooted device, it'll just bail out and crash. With that, it is much harder to get in the middle of it, try to tamper and modify things. In the original application, there was just a little bit of like string optimization. Like you saw the function names or some classes that were like the letter A, B, and C. Those do limit someone's understanding of what does what in the application, but it's not really enough. That's done by tools like ProGuard or R8. There are tons of optimization tools that will use a variety of techniques to try and optimize the application size, right? Like shrinking down string names, variable names, whatever, to the one single letter. That doesn't really protect your application, though. So let me tell you, this version of the app is provided by GuardSquare. GuardSquare does incredible work in mobile application protection. They encrypt, obfuscate, self-protect the applications, and I'm honestly really grateful for, hey, the approach they want to take with this video, and they're letting us showcase the techniques, the hacks, the real elite stuff, and not so much about, hey, the product or whatever, but I do want to show you that difference. What changes are made when you have a GuardSquare protected app? They sent this along, and it's incredible to see how it just totally knocks down everything that we've been able to showcase. And so much more. They've got DexGuard, they've got IXGuard, AppSweep, ThreatCast, all the sweet stuff for the different renditions, versions, platforms, languages you might find mobile applications in. So it's super slick, and I do want to sing their praises at least a little bit and really drive the point home. Look at how well this makes a difference. Like if we were to get back to the terminal, take a look. Here's our protected uncrackable secret safe. If I were to try to APK tool D to decompile that, try to manipulate Smalley, again, the byte code there. If I were to move into that directory, let me open this thing up in Sublime Text. Let's take a look at the Smalley folder for our Vantage Point uncrackable stuff with all of this. Well, for one thing, it's ginormous. You can barely make any sense out of the variable things and work that it does. However many lines we were looking at earlier when we dug into the Smalley code, I don't know, maybe 100 or so. Now this thing is getting up to 38,000, and that's only one piece, one bit. There is so much more here to get in the way. If some way, somehow, one actor were to make sense of this, find the right place to inject code in Smalley, a lot of the tamper detection and tamper prevention work that GuardSquare has put in place will find that, track it down, and then bail out. Let me see if I can drag in our protected APK from GuardSquare and see how well that will work. Let me go ahead and install this. Now I'll hide my face here so you can see everything. That should be installed. Now if I can open up our uncrackable one with the GuardSquare protected app, it is the exact same app. I could enter in, oh, the usual, please subscribe, try to verify. Nope, that is not the secret phrase here. Obviously, if I were to try and enter the I want to believe string, then we're looking good. Success, that is the correct secret. Now we can close out of this, and just for funsies, let's try and run Frida against this GuardSquare protected version of the app. I'll go ahead and uninstall this original protected copy. So let me get back into my terminal, and I actually want to make a copy of our protected APK, and we can call it, I don't know, whatever we want. How about like try to hack me.apk? And now following all the steps that we've learned previously, we can use objection to patch our APK with TAC-S to provide the source of our try to hack me.apk. It will cruise through this, start to inject, and oh, actually, it looks like it had a little bit of struggle there, but it did still bring together a new try to hack me.objection APK. So let's try to work with that. Remember, we will sign this with apksigner.bat. We can go ahead and enter sign with the key store of our environment user profile in the .android directory and the debug key store. Don't forget to include the APK, and you want the .objection APK file. It'll ask for the password. Remember, that is Android for debug mode. And now we have that signed with an id.sig included here in our directory. So now our copy of the protected app should have the Frida gadget injected in, but if I were to try to use Frida for real, actually run our Frida script with the hook str equals, given the uncrackable process that we want to work with, I can enter that and try to get it in action, but okay, we probably actually want to have that running. So let's hop back over to our emulator, now try to drag in our try to hack me objection APK. We can go ahead and install that. Bringing that up to run it though, I'll double click on our uncrackable one, but it crashes every single time. The protected GuardSquare app is actually detecting Frida, and it's not letting us run it. It'll crash the application every single time we try. We aren't even able to use our Frida script. Oh, sorry, here I'll bring my face back. Because the gimmick with Frida is that, look, you could have all these protections in the app, but then you run dynamically at runtime, it's still going to be unraveled. You add in these hooks, you add these claws, you add something in the middle of it, but you can't do that either. A rooted phone won't let the app run, and if we were to do the crazy tricks that we did to use objection and inject Frida into the APK itself, well, we'll see that change, the tampered modifications, and the app will still, again, not run. Frida itself can be detected, the hooks can be detected, all of these different protections are in place, and now we have shields up. So maybe that secret safe now really is uncrackable. At least as close to it as we can get with cybersecurity. Alrighty, well goodness, I think this has turned into quite a long video, but seriously, thank you so much for watching. Thanks so much for tuning in. I hope you learned something new. I had a whole lot of fun with this. Like, I've used APK Tool and JADX to look through the source code, but I've never actually got Frida up and running in action, and I've never been able to tamper with Smalley code and rebuild an APK. So I learned a heck of a lot. I sure hope you did too, as some sweet exposure to that whole wide world of mobile app hacking. And seriously, huge thanks to the sponsor of this video, GuardSquare. They helped kind of get my head straight on this, and honestly, it's just fantastic and incredible and cool to see all the protections, shields, locking the doors and windows, and doing everything they can to protect a mobile app. Please, if you are doing any of this development or you're digging into this, take a look, check out GuardSquare with the link below in the video description, and seriously, I'm looking forward to more. Thanks everybody, I'll see you in the next video.